Hopefully this is better. Yes. So good evening, ladies and gentlemen. This presentation will cover the modelling, design, manufacturing and testing of bifacial solar farms. This is an honest project that my team and I have worked on over the last 9 months. South Australia has between 2,400 to 3,000 hours of sunshine per year, as shown on this map over there. So this is higher than the global average, 2,150 hours per year. With the solar power available in South Australia, solar panel is a viable alternative for power generation. It would reduce our dependency on non-renewable energy such as fossil fuel and coal. But how do we optimize this solar power generation? One method is to use bifacial solar panel. These panels contain photovoltaic cells that will absorb solar radiation from both the front and back side of the panel as shown on this figure. The rear side of the panel will capture the direct and diffuse sunlight reflected off the ground and hence produce more energy than a monofacial panel, which is a one-sided conventional solar panel. So bifacial panels have been around since the 60s, but they were really expensive, so not many investors have looked into that yet. However, the cost of solar technology has decreased over the years, and this has incentivized installing bifacial panels in South Australia. The performance of a bifacial panel is compared with a monofacial panel by a company named Power Home. The test was conducted in California in May 2014. So the blue line represents the power output for monofacial panel, and the orange line represents power output for bifacial panel. The results show that the peak power output for bifacial panel is 15% higher than the peak power output for monofacial panel. The average production is also 24% higher than the single-sided panel as well. So although bifacial panels provide a high efficiency, they are also more expensive. Sorry about that. So like most renewable energy, bifacial solar panel is also location dependent. So what works in California may not work in South Australia as well. The aim of this project is to design a 10 megawatt bifacial solar farm for South Australia to investigate its cost and power output to see if it is more economically efficient than a one-sided solar panel like the one that we see around. A feasibility study was carried out to assess the cost effectiveness of installing a bifacial solar farm in South Australia. To measure the cost effectiveness, a parameter called levelized cost of electricity is used. It is defined as the total cost of a system divided by the energy produced over its lifetime. It allows comparison of net energy price for different power generation methods. A low levelized cost of electricity is desirable as that indicates the total cost of system is low relative to its power output. There are different configurations for solar panels, including fixed tilt, vertical, and tracker. For fixed tilt configuration, the panel is mounted at an optimal tilt angle. For vertical configuration, the panel is mounted perpendicular to the ground. And for tracker configuration, the panel will track and move and track the sun throughout the day. We wanted to see which configuration works the best for South Australia. So for the feasibility study, all configurations were considered for both monofacial and bifacial panels for comparison purposes. The plant size considered was 10 megawatt. In order to estimate how much power it will be produced by a bifacial solar farm in South Australia, a MATLAB model is developed. The amount of solar power captured by a panel is divided into 3 parts: direct irradiance, diffuse irradiance, and albedo. So direct irradiance is sunlight that reaches the Earth unaffected by the atmosphere, so it arrives from the direction of the sun. And diffuse irradiance is solar radiation that reaches the Earth's surface after it is scattered in the atmosphere. And lastly, albedo is a measure of how well the ground will reflect incoming solar radiation. Given the power output generated by the MATLAB model and cost estimation provided by commercial retailers, the levelized cost of electricity for different configurations are calculated. In general, vertical configuration is not applied for monofacial panels, therefore it doesn't have a value on the graph. The levelized cost of electricity for monofacial panels are higher than the benchmark values provided by the Australian Energy Market Operator. This is because some of the costs used in the modelling process are calculated based on retail price rather than commercial price from bulk buying. So this implies that the levelized cost of electricity for bifacial panels would be even lower. Based on the MATLAB model results, Bifacial panels consistently achieve a lower levelized cost of electricity than monofacial panels, with vertical configuration achieving the lowest value. This shows that it is feasible to implement that in South Australia. However, to verify this, collecting real-world data is needed because at the moment the solar energy harvested is just estimated using a MATLAB model. So in order to do that, 3 prototypes with different types of panels and configurations are designed and built. Starting from left to right, the first prototype is a monofacial panel system, which can be tilted at different angles. It is used as a reference for comparison between monofacial and bifacial panels. The second prototype is a vertical bifacial panel system, and the last prototype is a bifacial tracker system, which tracks the sun using a linear actuator. The dimension of each panel is around 1.6 meter by 1 meter. To test the 3 prototypes, a large and secure space was required. Multiple organizations were contacted, and the space provided by St. Peter's College best fit the requirement. Based on the MATLAB model, it is best to face the tracker and fixed tilt system toward north, while having the vertical system facing toward east. The prototypes are placed a meter apart to minimize the effect of shading, and due to the time constraint, the prototypes have only been tested for 1 week so far. So this is the graph of the theoretical results generated by the MATLAB model. For fixed tilt and tracker configuration, which are represented by the blue line and the orange line, they both have a generation peak at noon when the sun is directly overhead. And for vertical configuration, which is represented by the grey line, it has a double peak profile. This is because one side of the panel faces east in the morning, and that will create a generation peak, and then the other side of the panel faces west in the afternoon, and that creates another generation peak. However, our experimental data shows that all 3 prototypes display similar behavior. They all have a double peak profiles. This is unusual for tracker and fixed tilt configurations based on existing literature. These profiles consistently appear in all the test results, and it does not match the weather condition on the day of testing, as the panels were tested on sunny days with minimal cloud coverage. It is suspected the reason for this could be the electronic system just discharged the power to prevent it from overloading when it is fully charged. So the next stage of this project is to test how different site materials will affect the solar panel power output, since the amount of solar radiation that can be reflected back to the rear side of the panel is dependent on the albedo of surface material. On-field testing at a solar farm is also needed to get more accurate data. At the moment, the solar panels are surrounded by fences at St. Peter's College for security reasons, and this would cast shadow on the panels and reduce the overall power output. Lastly, a life cycle assessment will be carried out to assess the environmental impacts of each stage of the panel's life, from raw material extraction all the way to disposal. Bifacial solar farms have the potential to power Australia and eliminate our dependency on fossil fuel and coal. While a 10 megawatt farm isn't huge, this technology can be scaled up or down. There is also a decrease in land space required for using bifacial panels compared to monofacial panels. This will reduce land costs and other costs associated with land work as well, and labour. So going back to the map that we started this presentation with today, in Central Australia, there is even more solar potential, and there is a vast amount of land. This is an ideal opportunity for creating a new power network to meet Australia's growing energy demand. So before I end the presentation, I would like to acknowledge my team members, starting from left to right in the photo, down to Dan, Vernon, and Adrian. I would also like to thank my supervisor, Associate Professor Mazia Jamande, for his guidance and support. Thank you for your time.
Amazing presentation.
Thank you.
We appreciate the questions. If you have any questions.
Okay.
You got this.
Okay, so what time of the year did you pick to do this experiment or
So,
take a measurement there? Because the sun rotates, you know, that will vary your angle that you have to set your...
that is correct. So ideally with renewable energy, it is best to test it for at least a minimum of 1 or 2 years. But with Honours Project, we only get 1 year to do that. So at the start, we were planning to test for 2 months. However, because of different reasons, the frames were not ready, and we will have only been able to test for the last week. Yeah.
So it's been sort of spring, winter,
Yeah, spring, winter, and it was raining a fair bit last week as well. So the data hasn't been looking the best. But after this year, there will be another academic researcher taking over this project and continue with data collection. So hopefully, with that data, we can draw a more valid conclusion. Yeah.
I really like the graph with the cents per kilowatt hour there. Does that cents come from the construction of the panel?
That one. So the cents come from the total cost of the solar panel farm. So that includes initial investment, operation, and maintenance. So we calculated the labor cost to do the land work, how much concrete we need, the panel cost, the frame, and inverters, etc. Yeah.
How do you go about developing a theoretical model? What sort of variables do you look at?
So the theoretical model was developed by a team member of mine. I'll try my best to explain it. So I believe he did run the model for 365 days throughout the year, and we vary all the different 2 angles to see which one is the optimum one. So we have a lot of lines representing different 2 angles, and we'll see which one has the highest power output. Yeah.
Any other questions in the audience?
With the bifacial panels, do they just have PV cells on the back? Is it as simple as that, or are they more complex?
It is just as simple as that. So with the normal single-sided panel, they normally have a layer, and it blocks anything from entering that. So with bifacial panels, it's actually transparent at the back, so you can see the silicon cell from behind as well. Yeah?
So with albedo irradiance, has anybody ever attempted to put mirrors or other devices around to capture more sunlight and direct it back into the faces of the panels?
Based on our literature review at the moment, we haven't found anyone using mirror to try to reflect more solar radiation into the backside of bifacial panels. But we have found literatures on different types of concrete and different types of just material in general. So for example, snow will reflect a lot of albedo back to the backside, as you can imagine with the color white.
Sure.
And it wasn't included in this presentation, but for our project, we also tested the albedo of different site materials as well, so like quarry sand, concrete, and etc. So yeah.
Thank you very much.
Thank you.